Let's give it a warm welcome for Rob Krakhel, please.
I'm going to be loud.
Good. All right.
So I am going to talk about fluids in AP1, as well as some of the stuff that's actually changing with AP1, which has actually changed since the last time we've all spoken. If you were at the fall conference. Okay, so they've actually, I believe, solidified everything in terms of what the exam's going to be. So it should be fun. We're going to do a little hands-on stuff. We're going to definitely challenge you. You're going to have to think. I know, and that's why I like to preface it, because it is early, 9 a.m. on a Saturday. So that's that. So what are we going to do? I'm going to talk about what we're going to talk about. This is part one of slide one. Then we're going to talk about what's actually in the fluids part for AP1, what the reference table looks like so you can see what equations I'll actually have access to. Then we're going to try some questions, and I'm going to tell you what I do in my class and how you might be able to implement it in yours. Here's kind of the breakdown. Fluids is going to be 10 to 15% of the AP exam, which is about 3 to 4 weeks of class time. So talking to many of you, you just wrapped up the AP curriculum, or you're about to with 1 week left, which means you need another 2 to 3 weeks to do the rest of what you have now. So here are the topics that they say there are. Internal structure and density, pressure, fluids and Newton's laws, and then fluids and conservation laws. So if you're not familiar with the AP curriculum, they rely heavily on developing equations from free body diagrams and stuff like that, and then applying conservation laws or applying the change laws, right? So if dealing with work and momentum and all of that. And this is really the culminating unit for all of that stuff. This has momentum in it. This has energy in it. This has forces in it. This has a little bit of everything. Kinematics. The only thing it doesn't have is rotational, and we can be thankful about that because dynamics in fluids gets a little nasty when that happens. So they did something right. Here is what's on the reference table with regards to fluids. So if you haven't seen the reference table yet, they have it posted on their on the website. Okay, they have the whole guide for what will be in next year's stuff, and the main things on there that's useful, all right, is the atmospheric pressure stuff, which will come into play, and then these 7 equations. All right, I will tell you, having done this course quite a few times, you basically only see density as mass over volume. All the other ones are written in different forms. The other thing that they do really often is, instead of using rho in the question, they'll use capital D. I don't know why they're inconsistent with it. It does throw students off. I don't love it, but they do it. And you'll see that in a couple of the questions I have for you guys to try. On the overview, this is kind of how I break it down week by week. Density and pressure is 1 week. Statics is a week. Dynamics is a week. And then that's it. It's a wrap at that point. And I have not been able to condense this down more if you want to fit in all the experiments and stuff like that you really should. If you are not aware, all the tests are changing. The AP1 exam next year will be 40 multiple choice in 80 minutes and 4 FRQs in 100 minutes. So they just solidified that. They were on the fence for a little bit, but that's the breakdown. It's still weighted 50%, 50% though. So do with that information as you will. But that's enough talking. Very similar to as I do in class. Yes?
In your breakdown, you say, your basics and then the statics and then dynamics. Have you ever considered, or would there be any benefit to doing statics with statics in the rest of the course and dynamics with dynamics in the rest of the course?
Yes, and I'm going to talk about that. Yeah, there's a lot of breakdown that can happen here to implement this throughout the whole course. One of them is density, for example, which you're all going to have to deal with momentarily. Determine the density of Play-Doh graphically. You got 10 minutes. You've got Play-Doh, you've got rulers, and we have 2 massing scales. Good luck. So,
Another one. Share that.
So we got the scales in the back of the room, our balance.
I think what we want is at least like that's all there is size of like sugars.
So start off small. Get this consistency of this one. A small cube.
Oh
Not bad. As far as cylinders go. For 50.
I was going to come over and say hello. How you doing?
Very good. Yeah, my kids is keeping me busy these days. My kids are all Cub Scouts and Boy Scouts.
I used to love it.
It's pretty much a cube, so it's all going to be about the same.
All right, next one. We got this one.
And let's just cube it. Forget it. It's a cube. So what is it? 0.09? We're going to do 0.09 cube. Let's just find the mass and we'll do it that way.
So you want 3.5 cubes, right?
Third one is going to be 1 centimeter cubed.
And since I'm lazy,
See what its mass
that's
is.
42.87.
And mine was 58 grams.
Finding it graphically, so the slope of mass over volume, of mass versus volume is going to be the density, right? So you need several different masses, different volumes.
So, my guess is almost everybody realized you've got to do a graph of mass over volume. Okay, go ahead and look at your axes. Did you write on your axes mass and volume? Not yet. Unlabeled axes, it's fine. Okay, here's the problem though. What did you measure? Because you certainly didn't measure volume. Right? I didn't give you the tools to measure volume. I gave you a tool to measure length. Okay? Or diameter. Depending how you set up your stuff. Right? And so one of the things that they want on these exams and that the students get nailed for all the time, and it's their favorite phrase, is functional dependence. Okay, I don't think I've disliked the phrase more in my life in the past 3 weeks. But your measurements were dependent on what?
Ruler.
Right, the ruler. And so when you're doing these labs and you're talking to these students, what the AP wants, right, it's always one of the questions, design the lab to reduce the uncertainty. So where is the uncertainty here?
In the original length.
Okay, in your length, which is your measurement. So you want to reduce what? Number of measurements. And one person did it. Dr. Winters. Okay. One measurement, and I think Rich too, but I didn't see a lot of.
That's where I was going with it.
You want to hold that shape up? What is that shape? Which requires how many measurements? One.
Yeah, but you can't really accurately measure that.
Take a look at all your cubes, and then we'll talk about accuracy. I don't necessarily disagree, but it is one of the things that they want. But the other nice thing about this, right, is the equation for a sphere is what? Good, your students won't remember that. Okay, so it is on the reference table. But that r cubed is important, right? That r cubed tells you there's a linearization coming. Okay, in the AP, right, there's almost always a linearization question on there. This is a perfect example of a linearization that can happen. Now, I'm not saying there's anything wrong with making cubes. When I do this in my class, I let them do as they say choose. I have some groups that make all different shapes, and they're like, I did it this way. And I'm like, rough. How are you going to graph that? They're like, well, you can still get the volume. I'm like, of a cone. Brutal. You guys got this though, you know, don't let your dreams be dreams. But I've seen this on the exam as a sphere. And they like to do the linearization with it, and they like to talk about it. The other thing that we talk about, right, is the students sit there the whole time going like this with it. And as they do that, what happens to it? Okay. Loses mass. In some cases, it gains mass. This is why I don't take the Play-Doh back. It is yours. All right, your hands are the cleanest they'll be today, probably. It also heats up. So all of these things are things that we discuss that they don't necessarily think about. That was a big part of AP2. I don't know if it'll be such a big thing in AP1, but you never know. So those are just, you know, mass loss in this case is a thing. So when it comes to kind of the big ideas for these units, these are the things that I tell my students to think about for every question.
So if they did make a mass versus volume graph, is that points off?
Depends on the question. So depending how they word the question, they have taken points off for that. And the way that the grading has worked in the past, if it's like a 12-point question, graph will be worth 3 points. And one of the points will be, you've got to do these 5 things to get the point, and they'll often lose that point.
Could you just give me an example of how the question would have to be stated so that they have to do one measurement?
Normally it comes from the lab design, and I'll show you what those look like. And they'll tell you, they want to reduce this, you can only measure using this thing. You want to reduce error, the students are making spheres or something like that. They work it into the question, but the texts are often like this for those questions and very easily lost. But I have 2 examples of those, particularly the lab-based question, and I think the other one is the QQT style question that they ask. So I always tell them whenever you're doing these lab things, you want to try to reduce the measurements as much as you can, just to make them happy, but not the amount of measurements. The other thing I also tell them is you have to be specific with the amount of measurements that you're taking. I tell them the magic answer is 7, because if you say do a bunch of trials, they also won't give points for that. Yep, because they'll be like, well, that could be 3, and that's not really great, right? So I tell them 7. 7's the way to go with that. Yeah, but I've got a few. So hopefully that'll answer some of those. Awesome. Okay, and this is a lab that you can also use when you're doing force stuff, right? So you can work normal force and scales and all of that stuff with this. So this is not something you have to do on the tail end of the course. You can absolutely move it way earlier on. In fact, in AP, this might be something that you want to do, depending what you start with, this could be a first day lab. You know, look how fast you got into it. Your students should be able to do it too. The most irking part is when they start, they write D as M over B, and you're like, we're going to use rho, everybody. And then you give them the question, and they use D, and the students are like, but they use D, and you go, look, it's not me. I didn't decide, guys. All right? But these are the key ideas that I tell my students just to keep a lookout on. 1, pressure arises from particle collisions. That's still a part of this AP1 course. I don't know how they're working in the microscopic aspect of this and the macroscopic aspect. It made sense in 2. I can't say it makes so much sense in AP1, but it is outlined, all right? So I'm going to show you where that comes from, but essentially you can use momentum to work in pressure. It comes from the collisions, from that impulse. Pressure varies with depth. That's a huge one that comes up all over the place. Net forces arise from differences in pressure. So that's where you go from our normal mechanics into the continuum mechanics, right? That's the bridge there. Pressure is energy density. They really hammer this home. Huge on the 2 example. What does this part of the Bernoulli equation mean? What does this part of the Bernoulli equation mean? What does this part mean? What happens as you raise the height, as you lower this, as you widen this? They want energy diagrams. They want to know how the energy density changes. They want to know if you're a particle in that fluid, how is your stuff changing? So it's energy 2.0, right? So you get to do energy, and you get to do rotational energy, and then you get to do energy density. Okay, but if you stream it like that, it's not so crazy. The other two things I really love is system stuff. So for closed systems, energy is constant. So there is a big blurb on the AP1 guidelines about the difference between open and closed systems: conserved, not conserved, constant, not constant. And it is confusing. Okay? They're specifically like the system can be closed, but this is not constant, which doesn't really jive with what is taught in colleges. So that wording is super important, right? Because you can have a system that's closed for momentum but open for energy. So then is it an open system or a closed system if it's in the same problem? And their idea is, right, it's truly terrible. Their thing is, no, it's a closed system, the energy is not constant. And I'm like, think you missed the mark there, guys. It's okay. Just that's going to be really awful in college for them. But that's what they get at. And the other thing is mass. So conservation of mass is a huge part of continuum mechanics. Even though they talk about flow rate and stuff like that, it all comes from mass flow rate, which they toss in every now and again. They're like, what's the conservation law that does this? And all the students are like, conservation of volume. Doesn't work, okay? And if you want to show them that, what you can do is you can take 50 mil of a high proof isopropyl alcohol, 99% or 99% works best, and 50 mils of water. And if you mix them, you're left with about 95 mils of the liquid. And you can ask them, you know, where did it go? What happened? And actually the density changed.
Going back to the idea that the closed system of energy is not constant, do you mean that mechanical energy is not constant or just total energy is not constant? Because if mechanical energy is not constant, it doesn't bother me, but if it's total energy is not constant.
So they don't specify.
Okay.
That's the problem.
So it just throws kids off because it's like, why?
Yeah, because I agree. If it's mechanical, then you've got your concise, what you're talking about.
Yeah.
You
it's
lose.
still a fully closed system. It's just that,
Yep, but they don't.
They don't say anything, so the kids are just like, what?
Yeah, and when you're dealing with mechanics, you often don't get into the other types of energy, and that's a whole nother spiel. But they're very specific with their wording on questions, and they outline it in their new guidelines. So if you're off with that, you know, it could cost points.
When you do this lab, does each lab group get one of these?
Yes, generally yes. All of these, by the way, it was like $15 for all this Play-Doh. So it's not a huge investment. And I have an outline for some of the stuff you might want to have in your classrooms for next year. I outlined, you'll be able to see these. These are just what's expected of the students in each thing. I can boil it down for you. They've got to make graphs. They've got to do math. They've got to be able to argue it. That's what it breaks down to for each one. Then they get a list of experiments that you can do. I really just wanted to put this up here for this one. I really like that they put this in here for the average school. Have a student use a rope to raise an object 2 meters from the bottom of a 3-meter deep pool. Graph. So if anybody has and is offering up, I'd appreciate it's their recommendation. So you can go to your schools, tell them you need a teacher pool. They recommend between 0 and 4 meters. And then ask the students to switch and discuss. Raises a lot of questions, honestly. Here are the experiments that I recommend. I just put the names of them up there because there's a lot of different versions depending what you have in your classrooms. You just did the density of Play-Doh. Okay, you saw how simple that is. It does take about 40 minutes is what I give my students to do it. Because as they're going through iterations, I wait until they've got most of their data down before I go over and I ask them like, hey, you know, did you consider measuring it this way? And then they get infuriated. But that's part of the process, right? And that's some of the style questions that they give is, you know, you did it this way, but then this other student said this, so we're going to give you separate data to now graph. So I think it's important. The other stuff they do is density of an unknown fluid. So that only requires like a beaker and a graduated cylinder and then a scale. And you can use any fluid, oil, or stuff like that. Salted water, okay, stuff that you can have access to. They also like irregular objects. So that is an overflow. So you can fill a beaker up or a graduated cylinder basically up to the top, have it overflow into a different beaker or so, and then you can measure that displaced volume. That's another thing that pops up pretty often. They had a pretty nasty one, I think about 4 or 5 years ago on that, okay? Relationship between absolute pressure and depth of a fluid. That's a big one that they like. Buoyancy force. So that's a lab that you can do, again, with graduated cylinders. You can use force scales. I recommend kind of the weakest force scales you can get, 2.5 or 2.5 Newton, 5 Newton, 10 Newton's a bit much. And you just have them displace water with an object, and then you can plot it. You can have them get the density of the fluid around it, things like that. There's a lot that you can go with it. And then where will the water land, which is my favorite lab. I get a Home Depot bucket. I give each student a cup. I tell them they've got exactly 30 minutes to tell me where to place the cup. And their grade counts based on how much their cup fills. And it's great because even at the end of the year, they still believe me. And sometimes they'll place their cup slightly off of where the water goes and get nothing. And it's very satisfying. It's great. But I try to do about a lab a week, okay? One for me, but two, it's the best way for them to prep for those FRQ questions. Because the only way for stuff to come up is to do it.
Can you give me an example of how you do the fourth one down, relationship between absolute pressure and depth of the fluid?
Yes, absolutely. So what I do, and that brings us to this, one of the things I actually recommend is a pressure sensor. So in my school, we're fortunate enough to have the Pasco sensors. So what I do is I tape just pressure tubing to a ruler, and they slowly go into water, measuring the amount that it's below the water surface. And then we can work backwards, and we actually get the density of water from it. That's a question that comes up incredibly often on the exam.
So the pressure sensors, I don't have any, but that's a Pasco?
Yep, it's a Pasco thing. But there are alternatives. Fifox on the phone also works. So that is enough to measure pressure actually between the first floor of your school and the second floor of your school. So you can do it within your school. It's a little more tedious. Fifox, so Pyphox. It just gives you access to all the sensors on your phone. Next time you go to the city, as you're going under the river, go ahead and turn it on. It's very cool to watch it just spike up as your ears also spike up. But the other thing you can do, you can put that in a Ziploc bag. And what you can do is put some air in the Ziploc bag, seal it, and you can put masses on it. That will also read increased pressures, stuff like that. It is hard to do it without a sensor, though. I can tell you that. If you want to make a sensor, I'm working up a Arduino thing for that. I'm going to do a write-up. Hopefully that'll be out soon. You can make it for about $5, $10. So that's, you can do these things in the class. But the pressure sensors, I believe from Pasco, they're about 100 each. So truly awful. I'll be honest, even scuba sensor, stuff like that, they're not sensitive enough, and they're also expensive. So your kind of options are do it with the phone, or buy it or make it. Okay, but that's the one sticking point. Or give them the data and just talk about it. Okay, sometimes you got to do it. Okay.
There's also a FET. There's a FET simulation that does that.
That's true too. There is a FET. There's also Physics Aviary has a bunch of these that also work. They're all great if you need to use them, right? It's to get the point across, and that's really what matters. So this is roughly what I do, because I know that sometimes it's nice to see what others do so that you can try to do it. What I do is first day is density lab. They do the lab just like you did. That's the only explanation I give. Then we talk about pressure being force over area. We just do a couple things with that. We talk heavily about, what pressure is, how it actually works, what it means. Then we go into pressure from momentum. So impulse on a wall, you've got a bajillion particles that are doing this, and then from that actually arises something pretty significant. Then we do pressure as a function of depth, and I just do that as a lab. Okay, they derive the equation from the lab, and that's the extent of that we do. It comes back later with Bernoulli stuff, so we don't go too heavy into it. And then I give them practice or a quiz. I like to give them quizzes pretty often, whether I count it or not. I just call them a check-in, just to see where they're at, because If they get messed up from here, the rest of the unit is not going to go well. Okay, so if you catch it early, it helps. Then the second week, I go into buoyant force. This one we talk about in great detail. It's one of the sticking points that students have that we'll talk about, and then we do the lab from that. And we also talk about where buoyancy comes from collisions, the collision point of view, because that's popped up on the AP exam as well. It's in the guidelines, so my assumption is it's also in here. They've had you do free body diagrams, fluid volumes, all sorts of things, but that's that. Then we do the buoyancy lab. It's hard. It is a hard lab to do depending on the equipment that you have. If your force scales are not sensitive enough, if your masses are too dense, you get like 3 data points. Okay. I often have them do the buoyancy lab where you find the density of the surrounding fluid, but there's all sorts of ones that you can do. You can just do quick calculations where you have half of it submerged on a scale, and you can figure out what the scale reading is, figure out what the mass of the object is. You can make it work for what you have. Then we do a lot of practice questions here because it's a lot of free body diagrams. In AP2, we haven't touched a lot of free body diagrams at this point, depending if they came from Regents or AP1 in my school. In AP1 at this point, hopefully they have free body diagrams down. Otherwise, I apologize on their behalf for how your year is going. And then I give them a quiz. Okay, another just check-in free body diagram thing. That's that. And then we do flow rate stuff. So we talk about conservation of mass. We talk about how in a closed system, right, your mass should be constant. So your change in mass over time should be the same. In fluids, it's an ideal fluid, so your density is the same. That's where the volumetric flow rate comes from. So you can do V over T. Then you can get into work, right? So you pull that energy back in here. Work comes from the pressure differences in this case. Pressure times your change in volume. Then we go into Bernoulli stuff, and then we spend basically the rest of the time doing problems on that stuff until they understand it, and then they have their test. Okay, I try to confine it to 3 to 4 weeks, depending on the strength of the students, right? Because there's only so many days, especially now. So that's what I shoot for those. Yeah. Any questions so far?
You have a double period every other day or every day?
Every other day for this class. Now for AP1, I have every day is double. So it's going to be a little bit different for me, but for the single double, it's about 3 weeks. And I haven't been able to shorten it. So, but that being said, right, students should have a better understanding of momentum. Students should have a better understanding of energy, and they should have a better understanding of force diagrams and free body diagrams. So that should all be kind of in the forefront for next year.
So when you give the test, like this being at the end of the year, is this going to be like a cumulative test, or would it be just on fluids?
Every physics test is cumulative.
Oh yeah, we do that too.
Yep. We actually have a rule in our school that tests can't be cumulative. And I say, man, it's so hard to give tests. But everything is cumulative, especially towards the end with the FRQs. So I always try to give quizzes that have a little bit of everything throughout the year. And you should be able to hit everything with these, especially the momentum. The free body diagrams are all over the place, as are the energy stuff. Yeah.
Would you recommend this or rotation first, or does it matter?
Personally, I think I'm going to do rotation after this.
Okay.
Is my thought. Now, as somebody who taught during COVID where they chopped off the last 3 units for not going in their order and messed up a lot of people, it makes me nervous to do that.
Yeah.
But I do think that this before rotation makes more sense. Even before simple harmonic motion really makes more sense. If you go through old textbooks, I mean like 1900s and stuff, that's how they did it. But yeah, really I think at that point it's dealer's choice on how your times break down for the year. What fits nicely, what doesn't fit nicely. But I also do think that you can fit some of this stuff elsewhere in the curriculum so you don't have to do it so tight. So I do have a couple sticking points, but we'll come back to those because I do want to show you what some of the questions look like. So here's one of your, we're going to start off easy. We're going to escalate rapidly. All right, so what this says, an object is held in equilibrium submerged in a fluid by a piston. Which of the following is a possible free body diagram for the object?
So if we get this right, we get an extra Danish?
That's what I heard.
You gotta add up to zero. I'm trying to, none of them really seem like they add up to zero. Two down.
In the AP curriculum, they are drawn to scale as well. And so that has bitten my students several times because you may notice that two of these are nearly identical. And if you read it too fast, you got it wrong.
Number 2, you got 2 plus, and then it went 2 up.
All right, hold them up. What do we think?
Number 3.
I too believe in peace. Okay? It is choice 2. It is not choice 4 because choice 4 would actually not be in equilibrium. Okay? If you add Fg and you add force of the piston, it is actually a larger summed vector than the force of the fluid. That's why.
At least they put 2 before 4.
It's true.
But on the actual test, they put 4 first.
Yeah, right.
But you can see, right, that's the kind of stuff that they do. It's not just understanding the free body, but also understanding that nuanced, you got to do that. Now, the nice thing is next year, the students get 2 minutes a question. Okay, which means they get a whole extra 10 seconds to solve each one. So that's pretty exciting. So you can see some of these are pretty straightforward, right? These are nice freebie questions that I tell the students, this is great, you should be very happy. And then they escalate.
Rob,
yeah.
The labeling was there. It's fluid, piston. It's not like reaction buoyancy. That's the way they would label it.
Yeah, fluid, piston, gravity. Depending what else they have in there, they've had some really nasty labels. And inconsistent stuff with what you might use in class. So that's one of the sticking points that I say is, you can be on par with the textbook, you can be on par with some questions, but no matter what, they're going to use different variables for some stuff. Okay. So here's another one. A small rock sits at the bottom of a cup filled with water. The upward force exerted by the water on the rocks is F0. The water is then poured out and replaced by an oil, non-viscous, that is 3/4 as dense as water, and the rock again sits at the bottom of the cup, completely under the oil. Which of the following expressions correctly represents the magnitude of the upward force exerted by the oil on the rock? They really, really like Newton's third law for these two. Another question they may ask with this is, what's the third law pair? Okay, and the answer would quite literally be rock on the oil, but they'll also give, Fn on the rock, particle collisions. They've thrown electrostatic force in there before, so they can get pretty nasty with that, but I digress. Yes, I will tell you that the average for AP1 is about a 1.6 nationally, give or take. With only 5% getting a 5. Yeah. So the majority of students get less than a 3.
Yeah, 45% global pass rate last year. I think it's 55% a year.
But I mean, a strategy might be to take more time on questions that you know you're going to get right, or think.
So the challenging thing to that is knowing what questions are easy and what questions are difficult. Yeah. So this question is actually fairly easy. Okay, buoyant force is just rho VG. So the only thing that you're changing here is rho. You're taking it from 1 to 3/4, and so your force in this case would just be 3/4, choice A. Okay.
So they're ignoring air friction, air force
Yes.
on the surface.
Yeah, and it's a very, very valid point that was just asked. And it comes down to this wording, exerted by the oil on the rock. Because another question that they can ask here, right, is what is the normal force that's being exerted? Then you have to deal with the atmospheric pressures, you have to deal with the height of that fluid, you have to deal with all of that stuff. Coincidentally, this is a step up. I've removed your multiple choice options for this one. So you have to work this one out. All right, a child is holding a string of negligible mass attached to a spherical balloon that is floating above her head. Okay, or above her. I assume the head, maybe not though. Handstands are allowed. The balloon has a mass m when empty. The balloon is filled with a helium gas of density He and a radius r. So this is a case where they actually do use the rho symbol, but I'll show you one later. They use capital D. They release the string holding the balloon, and it begins to move away through the air, which is density air. A free body diagram is given to you, which is nice. And they want to know what the acceleration of it is. Now, this question will come in two forms. The very nice form, in which case you quite literally actually just use the free body diagram. The multiple choice would have FG or FB minus FG divided by M equals A, something like that. So I tell the students, look at the free body first, because your answer is probably in there. Or a question like this where that's not the case, and you actually have to go through and work everything out. Okay? Which, this is one of the sticking points that I was actually going to bring up, because how many densities do they give you? 2. Okay? And one of them is for the buoyant force, the other is for the mass of the balloon. Right? So what students often do is they'll go, oh, the mass of the balloon is m, except it's filled. Right? So the mass actually isn't just m, it's m plus the mass of the helium. So luckily it's a spherical balloon. That does make life a little bit easier. So now you have to throw in, right, the density, bless you, times the volume, times the g, the 4/3 pi r cubed, and the actual answers for this were about this long and about font weight. So they get a little nasty, and just like the other question, right, you'll have two answers that look very close, but one will use the density of helium twice. One will use the density of helium and the density of air. And so if your students read it too fast, they have 10 more seconds, so it should be fine. But if they read it too fast, they can get tripped up on that, and that's really what happens.
You said the answers were not in terms of volume, they were in terms of the 4/3 pi. Oh, that's fine. Okay.
Yes.
Okay.
Yeah, and they're long. This would be what, a four-term expression that pops up.
Yeah. Did they simplify? Like.
Okay. Yeah. So this would be, what would you have? You would have density of air 4/3 pi r cubed g minus 4/3 pi r cubed density of, or mg. Yeah, four terms. It's nasty. It's nasty. But it is what it is. You know? You guys want to work it out?
No.
Just remember that when you say that about all your students. Why are you not doing the work? But yeah, this is a pretty common multiple choice question that pops up. Here's another one. So these come back. The YouTubes. Okay, that'll confuse kids pretty good too. So liquids 1 and 2 have different densities. A U-shaped tube of constant diameter, both ends are open. So that's an important thing too, right? Because if it's open, you have to deal with atmospheric pressure. So I tell students they always have to check that. That is also a sticking point that happens. And they tell you the different densities of the liquid. One is 750, one is 1,000. And then they want to know which one most accurately represents this. And so I talk to my students, I tell them you can treat these like forces. Okay, you can think about these like forces, or you can think about these like pressures. If it's in equilibrium, right, both should be in equilibrium. And so you can deal with it that way. There's no numbers, so it shouldn't be too bad, right?
Take a while.
And as you can see, much like the free body diagrams, they did it here as well, right? So odds are you're between which two?
1 and 2.
1 and 2. And there's a very subtle difference between them both. Okay? 1, right, and 2 become a lot easier if you actually block out, and I tell this to the students, right? Anything that's equal in height, you can block out. And now you can deal with this in all sorts of different ways. You can deal with this, you know, in terms of they basically have to have the same forces downwards. They have to pair up. And so what are we choosing overall? What do we think?
2.
2? Okay, this is actually the point in the course that I actually like to talk about beer making. I teach seniors, so it's fine. Manhasset is an awesome place. But we talk about specific gravity, right, and what it actually means and how the hydrometers work, and a story of how I actually got into kombucha making. If you don't know how to make kombucha, use a thing called a SCOBY. It's a type of yeast, and it turns your sugar into alcohol. Now, kombucha is a very small percentage alcohol drink, or it's supposed to be, okay? It's supposed to be like less than 1%. Mine was 5, as it turns out. Delicious, but yes, the second fermentation with fruit turned out to have a lot more sugar in it than I had anticipated. But that's a direct, you know, I have a lot of engineering students, and I tell them all the time, you want to make money, you just have to invent the thing that everybody needs. And so somebody did that. Another common example is at bars, the 1 ounce pours, right? That's just a pressure valve. It lets 1 ounce go, then it seals itself. Every bar has about 300 of those things. Okay, there's about 30 bars just in Huntington where I live. Whoever made that, they're good for life. They can do whatever they want, right? So I tell my students, you got to be smart about it. The other types of questions that come up is stuff like this. So these are comparative questions. Students absolutely have difficulty with these, where you have to do ratios. So in this case, V wide over V narrow. The other thing that's challenging with these is this falls into 2 categories, right? This might be volumetric flow rate, or it could be Bernoulli's equations. Both of them, in Bernoulli's is a bit more visible because you have the 1/2 rho v squared term, so just the kinetic energy term, but it's a v squared. So they'll trip up on that. In the case of A1 V1, right, the area of a circle is what? Pi r squared, right? So you get that r squared over r squared stuff that also trips students up. So even though you go from r to 2r, and all of you just went, yep, my student's going to pick which choice? B, right? Because they're going to go ahead and miss the square. Okay, so the speed, right, of the wide to the narrow should be choice A. Okay, but they could easily flip this to be narrow over wide, in which case then it would be, right, D. You got that 4 in there. So I spend time at the beginning of the year doing ratio stuff like this with my AP1 students because it really helps them later on when we get to stuff like this. And I think it's worth it, okay, especially for things. I tell them write out all the terms because there's hidden stuff that you don't want to get caught with. Then you have some of the FRQs, which will come around. Okay, I printed these. There's two different ones. There's a statics one, and there's a dynamics one, so that you can see. I found them on the internet. But a lot of these have a couple things in common. The statics one that I gave you has springs inside of it. I think the two main things that they're going to overlap with the fluids and the new AP1 stuff is forces, absolutely. All right. The other thing that I think is going to be the big overlap is kinematics for the dynamic stuff. So if you taught me, you probably remember the water fountain problems and the water shooting problems, all stuff like that. That's what I think will come back. Okay. So. I will post solutions to these on that drive, but not yet, because just like my students, the best way to learn is to realize what you don't know, and the only way you can do that is to do them, okay, or at least look at them and get an idea. But that about sums up, you know, what I think may help as you start to prepare for this stuff. There is a ton of other stuff that is out there with all of this. As you start to go through it, you'll realize maybe what you don't know, what you don't remember, some of the sticking points that you have to go through. I did put these in here, so I'll tell you some of the places that they do get stuck. The collisions is definitely one of them. For momentum, they often forget that one of them, one of the velocities is negative, right? So it's not, as it turns out, a change of momentum of 0. It's actually twice, right? -2 MV. They'll probably put the cosine stuff in there because, you know, you can do that with AP1. But I don't believe that 2D momentum is on the AP1 curriculum. So
I'm sorry, they really get down to the particle collisions.
yeah, it's listed. It's listed in.
Interesting. Are there any examples of that from AP2? Like in a test or anything like that we can look at?
There are some that you should be able to see.
Okay.
And when they open up AP Classroom, there should be a lot in there. But most of the time, it literally just works down to impulse over area. So it's nothing crazy, but they like to ask, what causes somebody to float? And it's not just
done
buoyant
mathematically, not just conceptually on the momentum.
A little bit of both. Yeah.
Okay.
Okay. The conceptual is often it's just the particle collisions that's causing it, not this, you know, upward force.
Yeah. Interesting. Okay. I realize they broke the point down.
Yeah.
For 2D, it's you'll never have to calculate it, but you might see like a random like what direction would this go in. But that's like it.
If I've learned anything about the AP exam, is never say never.
Yeah.
The AP2 exam, some of the release questions had wave functions on them going through a barrier, which is not listed as one of the topics explicitly. So that's why I just say cover all your bases. You don't know what they're going to throw because they may sit there and go, well, no, it's really this thing that's causing it. It's like, that's a stretch, but you're in charge, so that's what that is.
It was a combination circuits with the resistors, I think they did. I think they said
Oh, yeah.
it shouldn't be more than 3, but there were examples of 4 or 5 or something.
Yeah. They're finally changing. That's what matters. I thought I had it outlined on here that they do, but they do explicitly say, I think it's in one of the sections about the collisions.
Okay.
They have to basically know what it comes from. Yeah, it's in there. The other thing that they have that they get caught on are the YouTubes. I tell them you can think of the pressures like forces, right? It's an equilibrium system. Pressure has some stuff to it, right? It's not a vector deal, so you have to tread lightly with that. But that's one of the things I use. The mass density substitutions, so density times volume for mass is all over the place with these questions. I imagine they're going to be snuck into other questions as well. Density in the buoyant force, messing up density of the object versus density of the fluid it's in. 110% going to happen. It's hard for them to understand the difference, but when it clicks, it does click. Volumetric flow rate from mass flow rate, okay, is another thing. They ask questions about this all the time. What conservation law, you know, shows this? And almost all of them go, it's energy. not energy. Okay, it's actually conservation of mass. But this one is energy. For the sake of time, I won't show you the derivation, but what you can do is you can take the energy equations that you have. I start it from work, so delta E is mg delta H plus 1/2 m Vf squared minus Vi squared. And then if you divide everything by volume, you wind up at Bernoulli's stuff. But the thing that they trip up on is when you do change in energy over volume, work over volume, force times distance over volume, you get out pressure. And so they talk about pressure as pressure. They also talk about pressure as energy density. And then they like to do graphs with that too, just like the energy graphs. I think some people call them the LOL diagrams. Those pop up. That was on last year's exam for AP2, just showing how does the stuff shift around. And then finally, Torricelli's theorem is another one that pops up explicitly on the exams. For this, you just have to focus the area of the opening on the top is way bigger than the area that it's coming out from. And so you can cancel out a whole bunch of stuff, and it basically leaves you with V is square root of 2gh, which takes you back to particle motion in energy. And that's that. That's my time. Okay. You can reach out to me with any questions.
Thank you so much. That was really very good.